Yeah, I think it's okay. Check them. Just refresh it once. Yeah, it's starting. Refresh it. Maybe wait for 3 minutes because others will also connect. Yeah, now it's okay. Right?
There's a time gap.
Oh, there's a time gap. Yeah. So, okay. That's nice. Hello, everyone. So this is Dr. Rijit Kumar De from IISER Mohali. So today we'll have a live session on the course Advanced Chemical Thermodynamics and Kinetics, which is being run in this semester and which is running in its 8th week. Yeah, so the idea of this live session is that we'll continuously interact with you. So you can come online, and if you have any query, you can always post it either here, or if you have queries later, you can also put it on the forum. And let me first introduce you to my TS. So we have here Ms. Shaina and Ms. Samita and Mr. Pankaj. So who are the TAs of the course. So they will actually give you an overview first of the course, and then at any point of time, if you have any question, you are most welcome to put it here or ask it. I hope you are enjoying the course. Thank you. But there is
Hello all. Welcome to the live session for the course Advanced Chemical Thermodynamics and Kinetics, which is an extension to the course Introduction to Chemical Thermodynamics and Kinetics. This course basically revolves around the fundamental aspects of physical chemistry, which are chemical thermodynamics and kinetics. So thermodynamics deals with change in energy, which is associated with various processes which we all encounter in our daily lives. So a physical system basically may possess energy in a variety of ways, which may be classified as kinetic energy. So kinetic energy is the energy which is associated with any body by virtue of its motion. Then we all are aware about what potential energy is. So potential energy is the energy possessed by a body in virtue of its position in a force field. And then thermal energy is the energy possessed by a body in virtue of its temperature. Energy which is possessed by a virtue of its constitution is called chemical energy. And then we are aware about the energy such as electrical energy and mechanical energy. So basically the motive or the object of studying thermodynamics is to seek out logically the relations between these kinds of energies and their diverse manifestations. So the laws of thermodynamics govern the transformation of this one kind of energy to the other one. And so there are various laws of thermodynamics. So basically the first law of thermodynamics is the most general statement of law of conservation of energy. So the law of conservation of energy is a generalization from experience and it is not derived from any principle. And then there are second laws and third laws of chemical thermodynamics. So second law basically deals with the direction of natural processes. So in combination with first law, which is basically the conservation of energy, the second law enables to predict the direction of the process and to predict the equilibrium situation. And the third law of thermodynamics deals with the entropy of the system. So a third law is used to So third law is used to basically talk about the randomness of a system and how the entropy is changing with how the entropy is basically changing in a system. So the statement of this law is that it states that the entropy of a system approaches a constant value when the temperature approaches zero. So this constant value is basically called residual entropy. So now my friends will tell you more about the course.
Hello everyone. So now we'll talk about how this field of thermodynamics started and how it is developed. So first of all, Sadi Carnot's in 1824 book titled Reflection on the Motive Power of 5 Marks, the starting point for the thermodynamics. It is a starting point of thermodynamics. He is the one who introduces us to the modern day of definition of work. So in 1843, James Joule experimentally founded the mechanical equivalent of heat. This led to the theory of conservation of energy and explained why heat can do work. And in 1850, Rudolf Clausius coined the term entropy to denote heat lost or turned into waste. And then in association with the Clausius in 1871, James Clerk Maxwell formulated a new branch of thermodynamics called statistical thermodynamics, which we have discussed in this course. So this branch of physical chemistry deals with the change involved in a process and whether a process is feasible, but it is important to know how fast or slow a process will be. Hence, it is important to study about the rate at which a reaction proceeds, and we talk about in this course of chemical reactions, the concentration of all the species present change with time, and so the properties of system change. The rate of a reaction is measured by measuring the value of any convenient property that can be related to the composition of a system and with time. So experimentally it is found that the rate of a chemical reaction is dependent on the temperature, pressure, and the concentration of the species present. From the study of the rate of a reaction, and it is depend on all these factors, much can be learned about the detailed steps which the reactants are transformed as a product. So now my colleague Pankaj will explain you further details of this course. Thank you.
So hello everybody. So my friends Saina and Samita had already told you about what basically thermodynamics and chemical kinetics is all about. So apart from just telling the spontaneity or the rates of a reaction, so chemical kinetics also predicts that how certain substance can drastically increase or decrease the rate of a chemical reaction. So usually we call such substances as catalysts or inhibitors. Now these catalysts play a very vital role in biological systems, in which most of the biological systems are controlled by catalysts. So we call these catalysts as enzymes in our biological systems. Also, many industrial processes rely on these catalytic processes, such as the Haber process for the synthesis of ammonia uses iron as the catalyst, so which increases the production of ammonia by a whole lot. Also, like determination of reaction rates can be used to determine the rate laws and rate constant of a chemical reaction. So from the rate laws we can find out whether the reaction is a zero order, in which the rate of reaction is kind of independent of the initial concentration of the reactants. Now the reaction could also be a first order, it could be a higher order reaction also. Now, experimental determination of any rate constant or rate law involves measuring how the concentration of a product or reactant varies with time in the reaction. Now, let's say, for example, we have the concentration of a reactant, and we can study the change of its concentration spectrophotometrically by measuring the absorbance of one of the reactant at a wavelength where no other reactant absorbs in the system. So also in the course, we talked about various techniques to determine rates of the reaction. So the techniques used to determine the rate of reaction have a very broad area. So they can be used. It takes minute or hour to rate, or reaction which occur on order of femtosecond, which we can't even imagine. So for measuring the reactions which are very slow, say the simple titration techniques are helpful for measuring those processes. But when the process occur on very fast time scale, say femtoseconds, then we need very sophisticated techniques for their determination. And we have introduced or we have talked about the ultra fast techniques of comprobe spectroscopy in that sense. Now between these two extremes, there are other timescale reactions which can be measured techniques, such as the stop flow method or the continuous flow method, which provide resolution up to microsecond or milliseconds. And there are stress photolysis techniques also, which can be used to provide that reaction rates on the order of few nanoseconds. So all these techniques are elaborately discussed in this course. So apart from all these, that experimental determination of rate loss for a wide variety of reactions also deals with a branch known as photochemistry. Now, what photochemistry is all about is that it combines the knowledge of light matter interaction with the chemical kinetics of any reaction. Now, this fundamental information about the molecular aspects of any system, and it helps us to understand the basic principle or the most underlying principle which we see in nature, like how the ozone formation takes place in the stratosphere, and how the process of vision in the human system or any being is seen, that how the cis to trans isomerization of the retinal takes place in the vision process. Now, a study of photochemistry involves the measurement of like optical property of the system under study. So the optical process or system. So the environment that we study or the environment around the system is also important for any photochemical study. So we study the photochemical system in solution phase, and we introduce the topic of solution phase dynamics in this course. So this provides information how the system or how the system is perturbed or the how environment use the optical properties of the system, and we then measure the optical properties of system as we vary the time of the reaction. Now, so far we have broadly we have covered these topics so far in the course. So further, the concepts of electrochemistry will be introduced in the course, which will tell you how the electrical and chemical energies are interconverted or how they are related to each other. So since we will be dealing with the conversion of energy between electrical and chemical energy and the changes involved, all these things, and the free energy associated with these kinds of reaction. So electrochemistry, broadly, if we categorize electrochemistry, it roughly falls in under the category of thermodynamics itself. So broadly, this is what the course is all about. We are already 20 minutes from the live session, so if you have any questions, you can post it here and we can answer your questions as per.
All right, so I hope everyone is enjoying the live session. So if you have any question, you can post it here. But meanwhile, we'll do another round of the overview of the course, which my TAs have already done. But if you have any specific question, please feel free to write it on the forum or here. So has there been any query or anything? Okay, maybe we can go one round of like discussion slowly. Okay.
So if you have any queries, you can post your queries here and we can answer them. So as we told you that there are basically zeroth, first, second and third laws of thermodynamics, which govern all the processes that we are happening. So the basics are if we talk about work and heat, so the concepts of work and heat are quite fundamental to thermodynamics, and their definitions need to be understood. So work is basically defined as any quantity which flows across the boundary of the system, and then so and basically several and heat is basically defined as the attainment of thermal equilibrium of two systems by asserting that a quantity of heat which is denoted by Q flows from one system of higher temperature to a system of lower temperature. And then we are already aware about what is the work of expansion and what is the work of compression. So in the earlier course, this course is basically an extension of an earlier course. This is an advanced course. So in that course, we have studied about how to derive the expressions for a two-stage expansion and a multi-stage expansion, and whenever there's a work of compression. And then the transformation could be reversible or irreversible. And then the processes which we talk about could occur at constant pressure or at constant volume. And there are certain important relations which need to be remembered, like change in heat, like heat capacity at constant pressure and constant volume. And the system that we are talking about could either be an ideal gas or a van der Waals gas or a real gases. So these expressions need to be talked about related to ideal gases, ideal systems, as well as real gases. And then for the determination of heats of formation, so I think you must be aware about Bon-Haber cycle, which takes into account a lot of processes like ionization and the electron affinity. And then the heats of formation could be determined for the process that is happening. So that is basically when we talk about thermochemistry.
So apart from just studying the absorption or emission properties in photochemical reactions or photophysical processes, a number of like processes happen in the molecule. So when a molecule absorbs light of visible or shorter wavelength than the energy gap between the two energy states, so there is a combination of vibrational, rotational, and electronic excitation. So the molecule doesn't simply take energy and go to an excited level and just emit the same energy what is supplied to it. So a number of processes happen in the molecule. So in such cases, if the energy is completely radiated in as light, so we call such processes as like radiative processes. But in some processes, there could be intramolecular vibrational relaxation in the molecule. So these intramolecular vibrational relaxations are very fast as compared to the radiative emissions, and these are dissipated as heat in the surroundings. So these sometimes the non-radiative processes like dominate the radiative processes, and in such cases the system is said to have a very low quantum yield. So, like if the molecule is very large or the molecule has a non-rigid structure, so the molecule can undergo a lot of vibrations, and the energy of excited state can be dissipated in non-radiative processes. These non-radiative processes could be like either intramolecular, which are collision-less, or there could be the intermolecular quenching of the emission, that is between two molecules. So uh, this intramolecular vibrational energy redistribution is known as uh, internal conversion. So this vibrational stretching of molecules is also important for the breaking of chemical bonds. So we know that there is a potential for any chemical reaction of for any electronic state for a molecule. So this is purely anharmonic in nature. So whenever we supply the vibrational energy higher than the bond dissociative energy, the bond simply cleaves, and which is the like most basic requirement for any chemical reaction to take place. So from photochemistry, we can also understand that how bond breaking and making takes place in any chemical reactions, hmm, which are the most important aspects of like chemistry. So now we are almost 30 minutes from the start of live session. So, but we didn't receive any questions. Okay. So if you have any questions, you can post it here, and we could answer in between our broadcast. So after the week for electrochemistry over, that let's say the 11th week, so we will also introduce you with some of the experimental techniques which we have studied throughout our course. So we have studied like say chemical kinetics. So in chemical kinetics we told you that the slow processes can be monitored during titration. So we have demonstrated an experiment in which the hydrolysis of methyl acetate is monitored using titration. So the reaction is very slow, so can be monitored during titration. But on the other hand, there are some vibrational relaxation in the molecules. Say we will take some highly emitting dye, so which has a very high absorptivity coefficient. So dyes usually have a very high absorption cross section. So we take a dye and we monitor the ultra fast dynamics of within that dye. So we told you that whenever a molecule absorbs any radiation, it also dissipates in form of vibrational relaxation. So we will see that as the time goes on for the emission will go towards the redder side because the molecule will relax vibrationally and come to lower vibrational state. So this the energy of this vibrational state will be less than the originally excited vibrational state. And when the molecule is fully relaxed in the excited state, it will be like red shifted as compared to its excitation wavelength. So this directly corresponds to what is known as Kasa's rule. So this we will demonstrate in a technique known as pump probe spectroscopy. So which will tell you how femtosecond time scale dynamics in a molecules are demonstrated or monitored. Further, we will also show like how steady state or single shot experiments, photochemical experiments can be used to monitor the reactions or the reactions taking place within a molecule just by shining light on them. So one of the system which we have taken is the photodegradation of a dye molecule. So whenever a dye molecule is kept in higher light flux or higher irradiation in presence of some photochemical catalyst, the dye usually degrades And since the chemical structure of the dye is changed when it degrades, so its emission properties are drastically changed, or its absorption properties are drastically changed, and its absorption cross section goes on decreasing. So we will monitor how with time the dye gets degraded. And also we talked about like diffusion properties in the course, or about transport phenomena in the course. So one of the finest example of diffusion property is the measurement of viscosity of any sample. So viscosity is generally how different layers of a liquid oppose the flow of each other. So when the liquid has less fluidity, we say that it is very viscous, and when its fluidity is very high, we say it's very low viscous liquid. So we will see that what parameters determine the viscosity of a liquid, and how to quantify these parameters of viscosity using a very simple instrument known as the Ostwald viscometer. So in the experimental section, we have demonstrated all those things, which you will see further in the course. Next.
So we have one question posted by Priyanka Tyagi. How can we explain work in irreversible is more or less in thermodynamics? So one quick answer to it is that for reversible process, we actually showed it in a pressure volume diagram, in isothermal diagram, and then we showed that the area under the curve actually differs for a reversible versus irreversible process. In the reversible case, so we said that the pressure is, for example, reversible expansion. If we just talk about expansion work, for that actually the pressure is reduced every step in infinitesimal way, so that the opposing pressure is nicely adjusted with the system pressure, or the system pressure basically adjusts with the opposing pressure in such a way that every step the opposing pressure equals to the system's pressure. And then you can actually use the ideal equation of state, and you can actually integrate the pressure into differential work done. That way you can show that it will be area under a smooth curve. However, if you do in a irreversible way for an expansion, so then it is basically work done against a single step or few multi-steps, where actually this number of multiple steps are countable. It's not infinite number of steps. So in that sense, the irreversible work will be more or less. So by the convention we chose here is that when we are working on the system, that's a positive work, and the system is working, that's a negative work. So positive work means actually work of compression. So for the work of compression, we showed that the external pressure has to be large. So for the same change in volume, you will have a larger area than the reversible work done. And the opposite thing will happen for the work of expansion, when you actually set the pressure all of a sudden with that of the final pressure, and then you let the system to expand. And then since the final pressure is much smaller, the area under the curve will be smaller, always smaller than the reversible direction, meaning if you go calculate the work of compression or work of expansion, it will be always the same. But you have to keep in mind that the reversible work means actually any reversible processes are idealized processes. They never happen in real life. So, but you can actually approximate a multi-step process where the number of steps are fairly large as an reversible process, or nearly reversible process, and all other processes will be irreversible process. So depending on the nature of the work, compression or expansion acts more or less than the reversible work. So the best explanation is can be given pictorially, which we actually gave. Maybe we discussed in this course a little bit at the very beginning, and also you can always look up the videos in the earlier version of this course, which is the Introduction to Chemical Thermodynamics and Kinetics. There we explained it in details, like how you can have a single step compression work or two-step compression work, and then multi-step, and then how you can actually reach the reversibility limit, and the same for the expansion work. So you can always go back and have a look at those lecture videos, and then you'll have a clear concept. You can also like consult recommended textbooks which have been cited in the course content. Anything else? So I'll just quickly review where we are right now. So the next, we have completed 8 weeks here, and the next week we'll be talking about solution phase reaction dynamics, because so far whatever we did, the models are based on gas phase reaction kinetics, where it was mostly based on the kinetic theory of gases. And then we'll talk about the solution phase kinetics, where you have like frequent, less frequent number of collisions between the reactant species in solution. And we'll talk about the solvation as well as electron transfer theory there. And next 2 weeks we'll be mostly focusing on electrochemistry. On the first week we'll be talking about the non-ideal solutions, where we'll be talking about first the what are the like how to tackle the deviation from the ideality, how to define actually or how to replace the vapor pressure by mole fraction, and the mole fraction by some quantity or the activity for the condensed phase or any solution phase reaction. And then we'll mostly talk about the electrochemical, what happens for electrolytes, because electrolytes, even they are fairly diluted, are actually a perfect example of non-ideal solution, because they deviate from ideality even at a very, very low concentration. So there we'll discuss the theory developed by Debye and Huckel for electrolyte solutions, how to calculate the activity coefficient and the mean ionic activity coefficient. And then we'll move on to talk about electrochemistry and the advanced topics. So I will be talking mostly about the ionic conductivity and details of the electrochemical cells, and a little bit about potentiometry. And we'll also give you a brief introduction on colloids and how basically coagulation and flocculation works. And it will be followed by the lab demonstration course, or basically a live, not live, it's basically recorded session on few select experiments, which Pankaj has already explained. And that will give you a feeling of actually how these kinetic measurements are done in real life. So this is an overview of the course. If you have again any question, you are most welcome to post it. We are here for some more time, and you can always post the questions later also on the forum, and we'll be happy to answer your queries. So, anything you would like to add?
Okay, so what is the reversible work done? For the reversible work done, we work against the external pressure. If that pressure is higher, then the work done will be higher. If that pressure is lower, then the work will be lower. Suppose if there is no external pressure, then what will be the work? Then in that case, work will be 0. So, and of course, in the case of reversible, the opposing pressure and the applied pressure, they are not much difference. There is no much difference, so the direction of the direction of the work can be changed. This is all about the reversible processes. And yeah, some of the people have like query like, can we change the date of the exam? So we are really sorry for that. We cannot change the exam date. So yeah, that is the for that you have to contact them directly. We cannot change the exam date. And while you are looking the videos, please look it very carefully. All the answers of the assignment you can solve by looking the videos very carefully, because the assignment which we made, that is all from according to the videos only. And yeah, when you are reaching to when your answer is like near about the options, then please mark the answer which is the near of the options. So please don't bother for that. It will help you in other exams also.
Since there are no more queries, we'll end the live session here, and you can post your queries, if any, on the ask a question or the answer. Hope you liked the live session and it was helpful to you. Thank you.